For the continuation of Chapter 5, we will now proceed to the compressive strength for torsional and flexural torsional buckling of members without slender elements. So here our nominal strength would be equal to the buckling stress multiplied by the gross area. We have here different conditions in deriving the buckling stress. So we have here for double angle and T-shaped compression members, and this is applicable when the flexural buckling about the x-axis governs. We also have here for other cases, like for doubly symmetric members, for singly symmetric members where y is the axis of symmetry, and for unsymmetric members. And reflected here are the formulas for determining the elastic torsional stress at x, y, and z axis. So to further understand what I'm talking about, let's open our NSCP 2015 where we derive these formulas. Actually, these are just the summary of what we had in the NSCP. So for you to be able to visualize where it came from, so you can open your NSCP on page 5-55. So page 5-55 states here the one that I'm talking about. So we have here the compressive strength for torsional and flexural torsional buckling of members without slender elements and the different conditions in the module. So these are the formulas and the conditions. We have also the formulas here for the polar radius of gyration about the shear center and the flexural constant H. But we can find these constants when we open our AISC book. But if you don't have the AISC book, you can derive the values of the polar radius and the flexural constant using these formulas. We also have here for members with slender elements, in which our nominal strength is also equal to the buckling stress multiplied by the gross area, and it provides here different conditions also. So we have for doubly symmetric members. So by the way, members with the slender elements experience two limit state, which is the flexural limit state and the torsional or flexural torsional limit state. So these are the formulas and the conditions. So to further understand this formula, or for you to be able to use these formulas, let us now proceed to our example. So verify the strength of a double angle 102 by 102 by 9.5 by 19 strut under ASTM A36 with a length of 2.5 meters and pinned ends carrying an actual dead load of 90 kN and live load of 250 kN. So for ASTM A36, Fy is 250 megapascal, Fu is 400 megapascal, and the modulus of elasticity is 200,000 megapascal, and the shear modulus of elasticity is 77,200 megapascal. So first step is to determine the required compressive strength. So under Lrfd, PU is equal to 1.2 the dead load plus 1.6 of the live load. So our dead load is 90 kN and live load is 250 kN. So it is equal to 508 kilonewton. And under ASD, our required compressive strength is equal to the sum of the dead load and the live load. So 90 plus 250 would be equal to 340 kilonewton. So the next step is to determine the slenderness limit, or let us check for the slenderness limit of this section. So the effective length factor is equal to 1.0 because it is pinned at both ends, and then the length is 2,500 millimeter. So determining the slenderness limit, or checking the slenderness under x-axis, so 1.0 multiplied by 2,500 millimeter divided by the radius of gyration at x. So this is the radius of gyration at x, 31.23. The next one, checking the slenderness at y, so 1.0 multiplied by 2,500 divided by the radius of gyration at y, so 49.25. So it is equal to 50.76. So they both meet or satisfy the limit, which is it must be lesser than 200, but we will use the larger value, so 80.75 will govern. Next is to check the slenderness of the element. Since this section is a double angle section, case number 5 will govern. So the width thickness ratio can be determined using this formula, and the limiting slenderness parameter can be determined using this one. So it falls under case 5. So determining the width thickness ratio, our B is equal to 102 and the thickness is 9.53. So the flange width is 102 here, and the thickness of the flange is 9.53. And then checking the limiting slenderness parameter is 0.45 square root of the modulus of elasticity divided by Fy. So our modulus of elasticity is equal to 200,000 and Fy is equal to 250 megapascal. So calculating it, is equal to 12.73. And we can say that the width thickness ratio is lesser than the limiting slenderness parameter. So this is a no slender element. So they both meet or satisfy the limit, which is it must be lesser than 200, but we will use the larger value, so 80.75 will govern. Next is to check the slenderness of the element. Since this section is a double angle section, case number 5 will govern. So the width thickness ratio can be determined using this formula. And the limiting slenderness parameter can be determined using this one. So it falls under case 5. So determining the width thickness ratio. Our B is equal to 102 and the thickness is 9.53. So the flange width is 102 here and the thickness of the flange is 9.53. And then checking the limiting slenderness parameter is 0.45 square root of the modulus of elasticity divided by Fy. So our modulus of elasticity is equal to 200,000 and Fy is equal to 250 megapascal. So calculating it, this is equal to 12.73. And we can say that the width thickness ratio is lesser than the limiting slenderness parameter. So this is a no slender element. So our section is a double angle, but this first condition will not be applicable because this will only be applied when the flexural buckling about the x-axis will govern. So we will proceed to the next condition, this one for all other cases. So since that is singly symmetric members where y is the axis of symmetry, we will use this formula in determining the elastic critical buckling stress, this one. So in determining the available compressive strength, where the nominal strength would be equal to the buckling stress multiplied by the gross area. So the buckling stress is equal to 0.658 raised to Fy all over Fe multiplied by our Fy. So substituting the values, is equal to 177.99. Oh, we can say that it is 178. Can round it off into 178 megapascal. So for flexural buckling limit state, you can now determine the nominal strength. So 178 multiplied by the gross area, and the gross area is 3,690 millimeter square. So the nominal strength is equal to 656.82 kilonewton. And under Lrfd, we will just multiply the nominal strength with factor, which is 0.9. Is equal to 591.14 kilonewton. And comparing it with our PU, which is only 508 kilonewton. So we can say that the section is safe. So under ASD, dividing the nominal strength with the safety factor under compression, which is 1.67, so it is equal to 393.31 kilonewton. And comparing it with our PA, which is equal to 340 kilonewton only, so this section is okay. So next is to proceed to the torsional and flexural torsional buckling limit state. So we will use the formula that I've showed earlier under section 505.4.2. So yan, our elastic critical buckling stress would be equal with this formula. Makikita nyo sa 505.4.2, yung pinakita ko kanina. So in order to determine the value of the flexural constant H, we will convert the section into English system. So our section is this is double leg, 102 by 102 by 9.5 by 19. So converting it into our English system, it would be equal to 2 leg, 4 inches by 4 inches by 3/8 inches by 3/4. Yan. Let's open our AISC manual for the flexural constant H and for the polar radius of gyration. So this is the properties of the section of 2 leg or double angle 4 inches by 4 inches by 3/8. So the polar radius of gyration is 2.49 and the flexural constant is 0.856. Yan. So the polar radius of gyration is 2.49 inches kanina. So converting it into millimeter, so it would be equal to 63.25 millimeters. And since we have our AISC manual, the flexural constant H is equal to 0.856, but if it is not available, you can determine the constant with this formula. So now the elastic flexural buckling stress about the y-axis is reflected here. We will just use the slenderness ratio at y-axis, which is na-solve natin kanina. So it is 50.76. So our elastic flexural buckling stress at y-axis is 766.1 megapascal. And ito naman susunod natin kunin, which is the elastic torsional stress, FEJ. So this formula naman. So yan, so opening your NSCP 5-56, these are the formulas for the elastic buckling stress for flexural, for torsional. So ito yung ginamit kanina natin in determining the elastic flexural buckling stress, and now we will be using this formula for the elastic torsional stress, wherein on this part we have a note here that for doubly symmetric I-shaped sections, CW may be taken as this formula, where HO is the distance between flange centroids. In line of a more precise analysis, for T's and double angles, omit term with CW when computing. So under page 5-56 of your NSCP, you can find here the different formulas for the elastic elastic stresses. Have this for X, for Y, and for Z. But take note here, this is the one that we've used a while back for determining the elastic fractional buckling stress, and now we will use the elastic torsional stress. And it has an important note here that for T's and double angles, omit term with CW when computing the elastic torsional stress, and take the coordinate X as 0. So we will substitute CW with 0. So let's try to substitute and see what's the value. So the NSCP provision says that our CW will be omitted when it is a double angle. So substituting those value, our shear modulus of elasticity is 77,200, and our torsional constant is 117,711.1. This one, the torsional constant, or the torsional constant. And area is 3,690, and the polar radius of gyration as from the AISC is 63.24. So our elastic torsional stress would be equal to 615.78 megapascal. So the values can now be substituted on this formula. We have now FEY and FEZ, and we have H. So direct substitution. Our H is 0.856. So calculating the values, it is equal to 490.18 megapascal. megapascal. And comparing it with 0.44 Fy para ma-determine natin kung anong gagamitin nating formula for the buckling stress. So it is equal to 110 megapascal. So we can say that that elastic critical buckling stress is greater than 0.44 of Fy. And since larger siya, FCR would be equal to 0.658 with this formula, Fy over Fe multiplied by Fy. So, substitute na lang natin yung mga values. Made-determine na natin ang nominal strength. So, yan. 250 is our Fy. And Fe is 490.18. So, it is equal to 201.94 megapascal. So, substitute it and multiplying it with the gross area na 3,690 square millimeter. Our Pn is equal to 745.18 kilonewton. And proceed now sa Lrfd. Multiply lang natin to with 0.9. So it is equal to 670.66 kilonewton, and this is larger than our Pu, which is only 508 kilonewton. And okay siya. And then for ASD, dividing the Pn with the omega or the safety factor for compression, which is 1.67. So it is equal to 446.22 kilonewton, and it is larger than our PA, which is only 340 kilonewton. So okay siya. So we can now conclude that the section is adequate. For the next example, determine if a double leg 5 inches by 3 inches by 1/4 by 3/4 long legs back to back under US customary designation under ASTM 836 with a length of 2.5 meters and pinned ends has a sufficient available strength to support a dead load of 45 kilonewton and live load of 135 kilonewton in axial compression. So for ASTM 836, Fy is 250 megapascal, Fu is 400 megapascal, our modulus of elasticity is 200,000 megapascal, and our G or the shear modulus of elasticity is 77,200 megapascal. So the first step is to determine the required compressive strength using Lrfd and ASD. So same procedure, 1.2 the dead load plus 1.6 of the live load. So it is equal to 270 kilonewton. And for ASD, 45 plus 135, or our compressive strength under ASD is equal to 180 kilonewton. So next is to check for the slenderness. So the effective length factor K is 1.0 since it is pinned at both ends, and then the length of the member is 2,500 meters. So the slenderness at X would be equal to our radius of gyration is 1.62. So converting it 1.62 into millimeter, so it is equal to 41.15. And the radius of gyration in millimeters is 1.33. So convert nyo na lang yan into millimeters. And in 1 millimeter or in 1 inch, there is approximately 25.4 millimeters. So since 74.01 is larger, we will use this slenderness ratio. So for the slenderness element, since the section is not symmetry sa legs nyo, or I mean the leg sizes are different, we will compute the width thickness ratio separately. So for the 5 inches leg, the width thickness ratio, so the flange width is 5 inches and the thickness is 1/4, so it is equal to 20. And for the slenderness parameter, so our E is 200,000 megapascal and Fy is 250 megapascal. So it is equal to 12.73. So the width thickness ratio is greater than our limiting slenderness parameter. So the 5 inches leg is slender. And for the other leg, the 3 inches leg, compute din natin yung width thickness ratio niya. So same procedure. So 3 inches and the thickness is 1/4. So it is equal to 12. And yung lambda R naman niya, parehas lang. So 12.73. Same as the one that we've solved earlier. So width thickness ratio is lesser than our limiting parameter. So the 3 inches leg is a non-slender element. The 5 inches leg is slender and the 3 inches leg is not slender. So opening your NSCP 2015. So our member or our section has slender elements, so we will focus on section 505.7. It has different conditions also that we need to satisfy, and also there is a reduction factor na nakikita natin on this formula. So here is an important note. For a cross-section composed of only unstiffened slender elements, QA is equal to 1, then it is equal to QS. For cross-sections composed of only stiffened slender elements, QS is equal to 1, then Q is equal to QA. And for cross-section composed of both stiffened and unstiffened slender elements, Q is equal to QS multiplied by the QA. And we have here for slender and stiffened elements on which we will use a reduction factor QS, and the reduction factor QS can be determined only depende kung ano yung nasatisfy na limit. So we have here the condition A, condition B, condition C. And we have also here for flanges, angles, and plates projecting from built-up columns or other compression members. Ito naman yung formula niya. Ito. Titignan muna natin kung ano yung isa-satisfy niya na limit. So, in order to proceed, we will determine the width thickness ratio, the coefficient for slender stiffened element or the KC, and then substitute natin dito, makikita natin kung ano yung mag-govern na formula for QS. So to proceed, let's start to solve for the width thickness ratio, and then let us solve the KC. And here the coefficient for slender and stiffened elements can be determined using this formula and shall not be taken less than 0.35 nor greater than 0.76 for calculation purposes. So yung KC natin, it must not exceed or it must be 0.35 to 0.76. And then if na-solve na natin yan, ma-determine na natin what will be our formula for QS. So let us proceed. First is to solve for the width thickness ratio. In which the B is equal to 5 and the thickness is 1/4. And then the next is to determine the coefficient of slender unstiffened elements or the KC using this formula as stated in the NSCP 2015. So our KC is equal to, by the way, yung thickness is this one, 1/4, twice the 1/4 plus the here inserting gap with 3/4 inches thick. And now limit must be within 0.35 to 0.76. But our KC is 2.58. So we will use the coefficient of slender and stiffened element as 0.76 kasi hindi naman siya pumasok sa limit natin. So let us now proceed to the torsional and flexural torsional buckling limit state, on which our buckling stress is or can be determined using this formula. So open your NSCP, makikita niyo doon, na-discuss kanina. And also, we will determine the critical torsional stress. This one, the FCRJ, the critical torsional stress, and the critical stress, na makikita niyo yung formula in our NSCP under section 505. So for the critical stress, it can be considered as the FCR. Na-note doon kanina sa NSCP. And for the critical torsional stress, it can be determined using this formula. So ito yung sinasabi ko sa inyo. So this is what I am talking about. So where the critical stress taken as FCR from equation 505.3-2 or 505.3-3 for flexural buckling about the y-axis of symmetry, and KL over R is equal to KL over RY, and the critical torsional stress can be determined using this equation. Yan. So our shear modulus of elasticity is 77,200. The torsional constant for this section is this one. I-convert nyo na lang into millimeter. And the area is 2,503.22. With our polar radius of gyration of 65.79. If you open your AISC manual, makikita nyo yung value ng polar gyration. And also with the H, or the flexural constant. So our critical stress, or critical torsional stress, would now be equal to 237.27 megapascal. Substitute lang natin. Yan. We have all the values now. Our flexural constant H is equal to 0.657. Yan. So direct substitution. So it is equal to 124.45 megapascal. And now we are ready to determine for the nominal strength by just multiplying it with the gross area. We have gross area here 3.88 inches squared, but you can convert it into millimeters squared, or you can open your CSI steel application. Makikita nyo doon yung area. So area is 2,503.22 square millimeter. So our nominal strength would now be equal to 311.53 kilonewton. So for Lrfd, multiply lang natin siya into 0.9. So it is equal to 280.38 kilonewton. And comparing it with our required strength, which is 270 kilonewton, yan, safe siya. So, okay, pasok siya. And then for ASD, divide lang natin siya into 1.67 or the safety factor for compression. So, it is equal to 186.5 or 0.54 kilonewton, and it is greater than our PA na only 180 kilonewton. So, okay siya. So, we can now conclude that the section we have is adequate and can withstand the loads. So the section is adequate.